Our third definition that goes with functions, or our third property with functions, is what's called a one-to-one correspondence, or a bijection. And it's basically built on our two previous definitions. Something is called a one-to-one correspondence, or a function is called a one-to-one correspondence, if it has both the properties of being one-to-one and onto. Functions that have these properties, both of these properties, are really, really important, because every time you have an x value, you know what its corresponding y is and that it's unique, and every time you have a y value, you know what its unique x value is. Because of this property, these functions are able to have what's called an inverse function. Let's look at some examples with arrow diagrams and figure out which ones are one-to-one correspondences. Remember, you have to have both the properties of being one-to-one and onto. When we look at this first function, f, that goes from the domain A to the codomain B, A maps to 1, B maps to 3, C maps to 4. Well, it is a function because every element here maps to only one element here. It is also one-to-one because each one of these, A, B, and C, maps to something different. So it is one-to-one. However, it is not onto, and it is not onto because 2 has nothing mapping to it. The range here is 1, 3, and 4, which does not match the codomain of 1, 2, 3, and 4. On our second example, we have a function g which goes from C to D. A maps to 1, B maps to 2, C maps to 1. This is not one-to-one because both A and C map to the same location. So we know it's not one-to-one. However, it is onto because every element here in the codomain is the image of something in the domain. How about this one, H, that goes from E to F? A maps to 1, B maps to 3, C maps to 1, C maps to 2. Is this one-to-one or onto? Ridiculous question. This one isn't even a function. And the properties of being one-to-one or onto are only properties of functions. So don't fall into the trap of trying to assign a property to a function of something that's not really a function. Here I have a function k going from G to H. A maps to 1, B maps to 3, C maps to 2. Every element here in the domain maps to something different in the codomain, so it's one-to-one. Every element here in the codomain is the image of something in the domain, so it's also onto. So this one has the very important property of being a one-to-one correspondent. That's important because if I were to give you any element here in the domain, you could tell me the unique element that matches up with it in the codomain. If I were to give you any element here in the codomain, you could tell me the unique element that it came from here in the domain. When you have this property, one of the things you can do is you can make all of these functions work in reverse. And we can make another function called k inverse, written this way, that maps, so k inverse of 1, for example, is going to map to A. K inverse of 2 is going to map to C. Only One-to-one functions have inverses this way, and that completes our three major properties that go with this section. Those three properties being a definition of one-to-one, a definition of onto, a definition of one-to-one correspondence, and for those functions that have a one-to-one correspondence, the idea of having an inverse function. Well, how about functions that are on infinite sets here? Real numbers times real numbers, like f of x is equal to 2x plus 1, which is a linear function that goes through 1 and has a slope of 2. Here we go. This is one-to-one because every element that I pick here on the x-axis corresponds with a different value on the y-axis. It's also onto, since every y value has an x value that maps to it. Since it's both one-to-one and onto, this is a one-to-one correspondence. And as a one-to-one correspondence, it's going to have an inverse function. What's the inverse function of this? Here's a way you can think of it. If this is the function, how do we come up with what is the inverse? Well, if you think of this thing graphically, this says y is equal to 2x plus 1. One of the things we can do, and that we did up here, is we switched the domain and the codomain, making this the domain and this the codomain. We just switched it the other direction. So let me switch the domain and codomain around by interchanging the x and the y values. And then what I'll do is I'll solve it for y. 2y is equal to x minus 1. So the y value is going to be x minus 1 divided by 2. So f inverse is going to be x minus 1 divided by 2. Or if you'd rather write it this way, it's 1/2 x minus 1/2. It's a line that goes through, what, negative 1/2 and has a slope of 1/2. All right. Let me give you another way to think of that. Do you remember back to where we had the inverse function? Or I meant to say the identity function. I sub x is equal to x. Going up here at this 45-degree angle. It crosses here. And this new function, the inverse function of x, is also going to go through this point. This is the line. F inverse of x is equal to 1/2 x as the slope minus 1/2. It crosses here at negative 1/2. The inverse function geometrically is found by flipping this function over the identity function. And we'll see how that works in the next section when we look at something called functional composition. Before we go on, I want to look at a little different kind of inverse function. Look at this function. F of x is equal to x plus 1 over x. Well, wait a minute. We can't have this function working everywhere because it wouldn't work if x were 0. So we're going to have to put a restriction in that the x value cannot be 0 because then we'd have 0 in the denominator. So we've made a restriction on the domain. What is the inverse function of this one? And I'm not going to get too much into how you would graph this, but what is the inverse function of this one? Well, we said over here that what we can do is we can flip the domain and the codomain around. So if I took this and said y is equal to x plus 1 over x, but x cannot be 0, and I switch the x and y values around, what would I get? I would get x is equal to y plus 1 over y. Well, now we want to solve this for y. I can multiply both sides by y and get xy is equal to y plus 1. I could subtract y from both sides, and then I can factor out a y to get a y all by itself. And then I could make y equal to 1 over x minus 1. Now this isn't going to work if x is a positive 1, so I'm going to have to restrict the domain here to being not 1. But you'll notice that what I have with this is I now have that the inverse function of this is going to be 1 over x minus 1, and it's very important to put on this section about x cannot be 1 to show the limits of the domain. So if we deal with limiting the domain in each case, we can talk about an inverse function to this type of function.